Good morning all, my name is Thavinnesh Kumar Rajendran. Today I will be presenting about quality and performance investigation of 3D printed ABS and PETG parts. These studies are conducted under supervision of Professor IRTS Dr. Sivarao Subramaniam. First thing first, to understand the title better, there are several questions arise. Among them are what is 3D printing, what is quality, what is performance. First of all, what is 3D printing? 3D printing or additive manufacturing is the construction of 3D object from a CAD model or 3D model by adding material, typically by layer. Well, for answer the question for what is quality is a product or process quality may be measured in numerous ways, including performance, dependability, durability, serviceability, aesthetic feature, perceived quality, and compliance to specification or standard. Next, there are several journals have aligned problems with the study. Among them are a variety of conflicting parameters that are affecting the dimensional accuracy individually or collectively. Second, dependence of the measured parameters are affecting the mechanical performance. Last but not least, ABS and PETG polymers are not suited for every printing application. The primary objective of the studies are: first, identify the quality and performance of 3D printed parts. Second, compare and evaluate the quality and performance of the 3D printed parts of ABS and PETG. Lastly, validate the quality and performance of the most stable 3D printed parts. The methodology of the studies are as follows. The STL file will be generated after the proper selection of 3D model. Following the selection of the material, which are ABS and PETG, the 3D model will be printed. Later on, the 3D model will be conducted quality and performance tests. After conducted the test, the result will be observed and analyzed using comparative analysis. The 3D model will be prepared according to tensile and flexural standard. For tensile, the standard are ASTM D638 Type 1, while for flexural, the standard is ASTM D790. As you can see here, this is the 3D printed of tensile and flexural specimen. There are two levels of process parameter involved. Among them are low level A and high level B. The low level has a printing speed of 20 mm per second, 0.1 mm layer thickness, and 180 degrees Celsius for extrusion temperature. While for high level, the printing speed was 40 mm per second, 0.3 mm layer thickness, and 220 degrees Celsius for extrusion temperature. To test the quality of 3D printed part, I have conducted two tests. The first test was surface roughness. This test was conducted using profilometer by taking the measurement of surface 5 micrometer. Each sample was taken 3 readings as shown in the image. Next was the dimension measurement. The measurement was taken using optical comparator. For tensile specimen, the measurement taken was width and height. For flexural specimen, length, width, and height was taken as a measurement. For each sample at each point, I have collected 3 readings as shown in the image. To test the performance of 3D printed part, I also conducted two tests as well. First of all, the tensile test was conducted using ASTM standard D638 Type 1, and for flexural test using ASTM D standard D790. Moving on to the result and discussion part, all the figures shows the image of test specimen after the completion of 3D printing. The figure above shows all the tensile specimen, while the figure below shows all the specimen for flexural. Let's dive into quality part. First and foremost, by comparing the surface roughness of ABS and PETG in tensile using high level parameter, ABS has the smooth surface finish than PETG. This can be proven by the graph above. As you can see here, the black color are indicating ABS while white color are indicating PETG. using a low-level parameter, PETG as the smooth surface finish compared to ABS. Next, in comparing the surface roughness of flexural, using the high-level parameter PETG as the smooth surface finish than ABS. This can be proven by graph above, where the PETG doesn't cross the value over 5. Using the low-level parameter, ABS as the smooth surface finish compared to PETG. Moving on to the next quality part, which is dimension, I've plotted graph according to the height and width of tensile while comparing the dimension accuracy of ABS and PETG. From here we can see that using high-level parameter, the ABS has the best accuracy than PETG. Using the low-level parameter, both stands to have an equal accuracy. By comparing the measurement of width of ABS and PETG in a high-level parameter, we found that ABS has the minimum error than PETG. From comparing the measurement of heights of the ABS and PETG in low level, we found that the PETG has the minimum error than ABS. Moving on to the dimensional accuracy for flexural, I have plotted graph according to length, width, and height by comparing the dimensional accuracy of ABS and PETG. From here, we can see that using high-level parameter, that ABS has the best accuracy than PETG. The black indicate ABS while white indicate PETG. Its same goes for low-level parameter. The ABS has the best accuracy than PETG. By comparing the surface roughness and dimensional accuracy, overall the ABS has the better quality than PETG. Next, the image above shows the tensile and flexural specimen after conducting the performance test. For performance, first and foremost, the comparison of Young modulus is must. This is because the modulus can be used to identify whether the solid is elastic or inelastic. The graph above shows the Young modulus for both material ABS and PETG and both parameter high level and low level in tensile. From the calculation, we found out that the ABS and PETG are in the range for standard Young modulus. As we can see here, our data shows that ABS has the lowest Young modulus, which means ABS is the elastic. By comparing the Young modulus between ABS and PETG in flexural, the calculation found out that ABS and PETG are in the range of standard Young modulus. From the graph above, we can conclude that the PETG has the low Young modulus, which indicate that these printed parts are elastic than ABS. Moving on to the comparison of tensile stress between ABS and PETG, the maximum stress was found in ABS material in both parameter high level and low level parameter, which indicate that ABS material can withstand high stress for it to break. Next, the comparison of flexural stress between ABS and PETG also indicate that the ABS material can withstand high stress for its break because it has the maximum stress. The figure left shows the stress strain curve for high parameter by comparing all the 6 specimens for ABS and PETG. From the stress strain curve, we found out that ABS1 has the maximum stress, while for low parameter, ABS3 has the maximum stress in all 6 samples. The figure left shows the stress strain curve for high parameter by comparing ABS and PETG. ABS2 has the maximum stress in all 6 samples, while for low parameter, comparing ABS and PETG, ABS2 has the maximum stress. As a conclusion, we can validate that ABS can be printed with higher quality than PETG and ABS has the higher performance than PETG. Thank you.